Hello guys, good morning. It's the first time we are filming in the morning because today is my off as Saturday Sundays are holidays in corporate. So we were on link list part. I think my screen is visible. Okay. We will be solving we have solved these three problems in the last train, these easy ones, and also the last problem from the binary search. Today we will target these medium problems from linked list part. So let's start with the first problem. Okay. So the problem says you are given a singly linked list, singly singly linked list. The list can be represented as L0, L1. Okay. Reorder the list to be on the following form. Okay. You may not modify the values in the list node, only node themselves may be changed. Okay. So basically, the question is saying that we have a list something like 2, 3, 4, 5, and we need to return a list something like first element will be from starting, then second element from the end, then from the starting, then from the end 4, then from the starting 3. So this will be the output for this list. For example, 1, 2, 3, 4. It is 1, 4, 1, then 4, then 2, then 3. Simply for 1, 2, 3, 4, 5, it is 1, 5, 2, 4, 3. And also we can't modify the values in the node. We just need to manipulate the pointer. So yeah, let's think how can we do this. This pointer should point on the last pointer. Then the last pointer should point on the two pointer. Then this two pointer should point on the second last pointer. Then two last pointer. Mm, okay. So we have this values can be number of nodes are 10 raised to the power 4. Okay, it's smaller than this. I'm thinking of a solution in which we don't need extra space. Means we can just do it in big O and time and without using an extra space. So I'm looking for that solution. Okay. 1 to 5, 5 to 2, 2 to 4, 4 to 3. How to make a track of last element. Mm, mm, Okay, so I am thinking of a solution in which I will reverse the half of the linked list. I will reverse half of the linked list. Mm, okay, I'm thinking of reversing half of the linked list. Suppose if I in this case if I reverse this half linked list, and then I can uh, backtrack from the last position, because after suppose my tail head will start from here, then my head need to point to tail. Okay, then I will my move head here and my tail here. Okay. Okay, so then my tail will point this pointer and I'll move tail here, and then my head will point uh, this pointer and I will move my uh, tail here, sorry, head here and tail to also this position. So I think that can work. Mm, means reversing half of the list node. So in order to reverse half of the list node, I need to find the middle element, and after that middle element I first need to reverse that part, and after reversing I need to apply the logic to reverse the linked list. So this is also I think this is a very complex logic. So working on a list 0. Okay, 1 2 3 4 5. Moving my this part. Tail part, tail. It's not tail. Look next. Mm, next equals to temp. Tail equals to tail next. So temp will be at this position, tail will be at this position. What I will do is I will do here this here. This to this part and this to this part will become equal. And the left line tail dot next will be tail. This will go here. This will go here. Tail will become this part. This will go here. 10 will go here, tail will go here, and ten pen tail. Okay, so I'm thinking of reversing the half of the list. In the case of odd, I will reverse this part only after the middle element, and in the case of even, for example, this case 1 2 3 4, I will reverse this part only. Okay, so in that case, what I'll be having is the advantage which I will be having is that I will have a pointer at the tail position, so I will be able to backtrack this. Initially, I will be able to add 5, for example. First, I add 1. After adding 5, I will be able to move to the fourth position by using next pointer. So that is how reversing half of the list will help me. So what we will be doing here is first we will be calculating number of node in our list, and then accordingly we will be uh, reversing our half of the list. So I think this is kind of a solution which is complex but has I think has a better time complexity. Means here we don't need to use the extra auxiliary space. So let's try if it works or not. So um, let's define a variable, temporary variable, while our temporary variable is not null. Okay, so what we will do here is we will count the number of nodes which is 0 initially, and we will increase our n and move temp to temp dot next position. So at the end we will so this will count our nodes. Okay, so we can also use another function, so similar to count nodes, where we can pass this temporary variable, and we can something like temp int count nodes in list node and define int nodes as 0, and we can put here something like nodes, and at the end we can return nodes. So yeah, this function will count a number of nodes. Okay, so we have counted number of nodes, so we need to find this middle element, this element. In the case of order list, we need to find this element, and in the case of even, we need to find this element. So basically this will be 5 by 2, so 0 1 2 at the 2th position, 4 by 2 2 0 1 2, this will be at the 2th position. So we just need the n by 2th element at n by 2th position, that will be our middle element. So let's set a count that will be equal to, so while our count is greater than, okay, so let's reinitialize temp to head. So we have reinitialized temp to head, and we will find middle node now. So while our count count is greater than 0, what we will do here is we will move our temp to next position and will decrement our count. So suppose here our count is 2. So we go here, we check is our count is greater than 0. Yes, it's greater. So we move our pointer here and our counter becomes 1. So we will check if our counter is greater than 1. Yes, it's greater than 1. So we'll move our counter here and decrement 1. So 0. So we will check if our counter is greater than 0. No, it's not greater than 0. So this is our middle element. Okay, so this temp node will simply indicate that this is our middle. So we can also do something like list node. We can name it as middle. Wait a second. Middle, and we can uh, initialize a function which will find our middle. Middle will be at n by 2th position, and we can pass the what we can pass pro. We cannot pass head. If we pass head, then it will cause some issue. So we will reinitialize our temp to head, and we will pass temp here. And we can what we can do is we can make a function public this node find middle count. So we will return the temp here, so that will be our middle position. So this will give us middle node. Okay, so we have also created a function to find the middle node. Let's drive it because we will use in this class only. Okay, so let's just print our value of the middle node so that we can verify that our middle node are correct values. So middle dot value, let's run. Okay, we are getting some error. System, okay. Where's the count, bro? Okay, we already have count, so we don't need count variable here. Okay, so we got our middle value here is 3, which is printed 3, and here also we got our middle value is 3. So till now, till this implementation, we are moving towards right direction. So now we need to reverse our linked list from this middle position. So yesterday we have done the question to reverse a linked list. So our middle will act as the previous element in that implementation. So let me just find that implementation for you. That was to reverse the linked list. A reverse linked list. Okay, so we have implemented the linked list. Okay, so let's just write here that reverse linked list. Okay, so we have taken our we were actually reversing our full list. So we were taking previous element as the null. So instead of previous element taking as null, we will take here previous element as the middle and current element as the middle dot next. Okay, so let's yeah, so that will at the end our previous pointer will be the will be at this position, means it will act as our tail. So let's mark it. This is our previous pointer, so at the end our tail will be this previous pointer. So let's check if our print ln our previous pointer is going to our tail value or not. Tail value will be 5 here and 4 here. So let's try running this. Okay, we got some error, so we need to add this temporarily to found cycle in list node. Oh, no need to worry. So basically 4 is our tail node and 5 is our tail node. So basically we are getting a tail node. So this was our previous value, middle value. This is our current value. Let's try run our reverse linked list function. So this is our middle value. This is our current value. This is previous value and this is current value. What we will do is we will store our this part current dot next, and we will move current dot next to our previous part. Okay. One thing I think we also need to do here is if we do have previous values pointer, then we should mark previous dot next as null. That will remove cycle from our list. So yeah. Yeah, so now we don't have any cycle in our list. So basically we are returning 1 2 3 because we have set 3 2 as null. So this part is to remove the is to reverse the linked list. So now we have list in the form this, our previous pointer at the tail and our head pointer at this position. So now we need to construct a we we need to reorder the our list. So now the real implementation will start. Can we use a separate function for this also? So let's see. So private void reverse reverse list. Reversing list will take, I think, how much variables we need. We need a middle. We only need a middle pointer that will do the job for us. So let's cut this from here and print here. So our tail node will be after reversing the list, we will get our tail node. Okay, so let's print the value of our tail node, tail dot value. Before that, our function needs to return a list node, so we'll return a previous pointer. So please first try to implement the reversal English question. So after that, you will be able to understand this implementation. So okay, mm, but what we are getting wrong here then? Okay, we are getting our tail node. The implementation is going pretty long, so there must be a solution which is smaller than in this implementation. So our main implementation will start. We will reorder our list. So okay, I will call. I will reinitialize my temp pointer to my head pointer. Okay. So now my temporary pointer is a head pointer, and I do have a tail pointer. So I will reorder my list. I will assign this value to my tail value. Then I will move my tail value and move my temp value. Then I will again assign this value to this value, and similarly till I get a position where my tail and temp node become equal, not equal to tail value. So what I will do is I will initialize a temporary head, which will be temp dot next. And what I will do is I will move my temporary pointer to my tail node and move my temp pointer to my temp head pointer. So what I have done here is I have moved this next part to 5 to this 5, and I have moved this pointer from this position to this position. So now my tail pointer is at this position and temp pointer at this position. So what I need to do now is I need to store restore temporary tail as the tail dot next. And what I will do now is I will make 5's next value as the current temp. So which is tail dot next as the temp value. Okay, and will move my tail to this position 4. Mm, tail to temp tail. Okay, so I think this will work. Let's try running this. Okay, at the end what I need is tail dot next to be null. Okay, because next is null. So in the case of 4, we are getting an error here that we don't have a tail dot next. Our tail value is null. So let's see. In this case, I will have list something like this. I will have list something like this. So my tail pointer is here, my head pointer is here. So what I will do is I will move this pointer. I will assign this value to this value, and then this tails value to this value. Okay, tails value to this value. To this value, and my tail pointer is now at this value to this value, and this value next value I will store here and assign this tail dot next to my temp value 142. Okay, so now my temp is at this position and my tail is at this position. I will find my temp dot head as tail dot next, temp dot next. Okay, what I will do is I will assign this to my tail value. Okay, and move my temp to my tail value itself. Okay. And what I will do here is my tail dot next. So this pointer does not have any next. So this will be null. Okay, so I need to check if my tail dot next becomes null. I need to break my while loop. I think this will work. Okay. Can we try to submit this? Let's try. Let's try. Okay. We got 87% faster solution. But I think we have done a lot of code. This can be, I think, done in a 4 to 5 lines. That four-liner solutions. So we have solved this problem in 34 minutes. So yeah, in an interview this will work. Can we ask ChatGPT to prettify this solution? Prettify to uh, follow oops principles and a bit cleaner. Let's take out this. Okay. We'll check. Find middle. Okay, I have forgot this implementation to find middle to use slow and fast pointer approach where we don't need to uh, calculate the middle value. Okay, fast and slow pointers. With the help of this, we can calculate this. Okay, list node second half. We have find middle. We have given middle dot next, and we are getting second half, and we are using the concept of merging two lists. Okay. Okay, bro. Pretty great solution, I think. Yeah, I think GPT has given us a better approach. Means approach is same, but it's just neglecting this function count node. In middle function, it is using slow and fast pointer. So to find the middle in the only one iteration. So yeah, that was good. So I think we can move to the next question, which is remove nth node from the end. Let's open this. Okay, so we are given a list, given a linked list. Let's just hit the timer button first. Okay, so we are given the head of a linked list. Remove the nth node from the end of the list and return its head. Okay. So in this example, we need to remove a second node from the last. So first node, second node. So we need to remove this node from the last and this node from the last. Okay. Okay, this node from the last, and we then need to return the head of the list, basically the list after removing the this element. Okay, so the number of is the size this. So n will be n is a valid value basically, and we can have in total 100 nodes. Can you do it in one pass? So the question is requiring us to do it in a one pass. So I think the first approach we can use here is where we can simply reverse the list, and we can remove. Wait a second, I'm getting a call, guys. Okay, so in brute force approach, what can we do is, listen me guys, brute force. We can reverse list. Okay, suppose we have this list: one pointing to two, two pointing to three, wait guys, three pointing to four, four pointing to five, and our n is two. We need to remove second node from the last. So first what we'll do is reverse the list. So after reversing, what we will get is, we'll get a list like this. Okay, two, three, four, five. Okay, now what we will do is we will remove now our head will be this pointer. So we will remove second node from the starting. So remove second node from start. Remove nth node from start. Nth node. Okay. So after removing nth node, what we will get is something like this. Two, three. Okay, we have removed nth node, so now we don't have four. So yeah, this will be the scenario. Now we will again reverse our list. Reverse list, then what we will get is one, two, three, five. Okay, so this is the one pass, this is another pass, so we are taking two passes to uh, find the solutions. So I think we can first implement this brute force solution, then can move to the more optimized one. I am not able to think of any optimized solution. I think from the previous part we can take a middle pointer or something like that. Let's discuss optimized solution. Means figure out the optimized solution. Optimized solution. So we have this list: one, two, three, one, two, three, four, and five. Another one is one, two, three, four. So here is slow pointer, here is fast pointer, then slow pointer will be here, fast will be here, and slow will be here, fast will be here. So in the case of E1, sorry, old, fast or next becomes null, count becomes middle position, means count. Okay, so basically count will become into 2 minus 1. Okay, in the case of this slow pointer, fast pointer, slow pointer will move to here, this position, and fast pointer will move to this position. Slow pointer will move to this position, fast pointer will move at the null part. If our fast becomes null, then that is the even case. If fast dot next becomes null, that is the odd case. Okay, and in this case, number of nodes will be count minus 1 into 2, and here into 2 into 1. Okay, so we have decided middle. So on the left we have this much node, on the right we have this much node. So we have figured out number of the node from this position and number of nodes from that position. Okay, so what will we do here is we will use fast and slow pointer approach to find middle index. After finding middle index, we will check that how many steps our slow pointer took to reach the middle position. Suppose it took n steps. Sorry, k steps. Then in the case of even total nodes will be in the case of even we will reach this position. So then our total node will be k minus 1 into 2. Okay, into 2. So this much nodes we will have in the list. And in the case of when in the case of odd, the total number of nodes will become, so this was our k. So total nodes will become we will multiply this position by 2, k into 2 minus 1. So this will be total node in odd. So we can then decide that our node which we need to remove is existing on the right side of the pointer or is existing on the left side of the pointer. If it exists on the left side of the pointer, we need to move our head pointer to remove a temporary pointer from start to remove that node. If exists on this side, so we can use our this pointer itself, middle pointer, to remove. So that is how we can do it in one pass. So basically how it is a one pass. So our slow pointer will move till this position, so that is the half pass, and in next half pass we can remove the on nth node. So half pass plus half pass, that becomes a full pass. So that is the optimized approach. So I think we should implement the optimized approach directly. So let's define our slow pointer. Slow pointer is at head position, and also fast pointer is at head position. Okay, so while my fast pointer is not equal to null, my fast pointer is, as you know, is fast, so it will become null first. So we will only check if our fast pointer is null or not. So we will check fast dot next is not equal to null. Okay, let's just also maintain k variable. So okay, so we will move fast pointer to fast slow pointer to its next position. Slow one step ahead, fast pointer to fast dot next. So that is why we are checking that fast dot next is not null. So we don't dereference a null pointer. So we will get the number of nodes in the left half. So let's print this first. Okay. Mm, let's return null for now. वैसे we will be returning a head at the end, so no problem. So we have a list. So let's find this, add these two test cases. First is this, okay. Second is this, okay. Odd case and a even case. Let's run. Okay, so we are getting 2. Oh, we are getting index 0 1 2. Okay. Or we can say we have this much value on the right side. Yeah, we can say. But here we can't say that we have this much values on the right side. Okay, we are getting a 2. Can we make this a 3? Can we make this a 3? So we can start our k with 1, and suppose let's find number of nodes. So what does n represent? Okay, so int, let's also define a variable total nodes, which is 0 initially. So I will check if my fast pointer is null. In that case, my fast pointer will become null in the case of I have just dry run this function, so that's how I was able to figure out that. Where's the my observation gone? Okay, so my fast pointer will become null in the case of even. So in the case of even, what, how can we find the node? Total nodes as k minus 1 into 2. In the case of odd, our total node will be k into 2 minus 1. So let's print the total node. Total node. Okay, so we have 5 total nodes here, which is true. We have 4 total nodes, which is true. Okay, so here our middle pointer is at third position. Here our middle pointer is also at the third position. So basically slow pointer is our middle pointer. So now we need to decide that the node we which want to remove exist on the left part or on the right part. Okay, so one thing we can also say is we were printing our k also. So let's just do a observation. That observation was that uh, position of k is 3. So basically we have three nodes. We have three nodes before the slow pointer. So this is our slow pointer. So we have three nodes before the slow pointer, and here is our slow pointer, and so also we have three nodes here. So why don't we directly compare our n with the k? So if my n is greater than k, in that case greater than or equal to k, in that case node which we need to remove exists on the left part. Otherwise it will exist on the right part. So let's take this example only. So our n here is 2. So our n is smaller than k. Basically k is 3, so n is 2. So we can say our node exists on the right part. Okay. And here our n is 2. So we can say our node exists on the left part. No, no. But this is the even case. So our slow pointer is here at the third position. I think we need to calculate the value. What if we take 0 then? Suppose we are removing this node, fourth node, then we need to start from the this position. If we need moving this node, we also need to start from this position. If we removing this node, we can start from middle position. So till these positions, this is 3 middle position is. If it's smaller than 3, then we can move in it right. Okay, in odd part this will work. If I take k as 1, okay, let's say even part. If my node is at this position, mm, middle is at this position, and I need to remove this, so I also need to move to the right position. So k is 3. Mm, 1, 2, 3, 4. K is 3, and n is equals to 2. K is greater than 2. Okay, so my k is 3 is greater than, my n is greater than 2 here. Mhm. 1 no problem, 2 becomes no problem, and 3 becomes, in the case 3 if we become equal, left part. Okay. Here it's 3, 1 no problem, it's become 2. Suppose we want to remove the third position, so 3 position greater than equal to, so it will be removed from the left side itself. Okay. Hmm. In the even, suppose I, case of even, in the case of even, suppose I move my pointer to this position, if it's equal to or greater than k, in that case I need to move from the right part. And how much I need to move from the right part? Suppose it is 4. 4 and my k is this. Mm, let's figure out the total nodes. This. Okay, so these are the total nodes. And we need to remove nth node. So I have 5 node here and my k is 3. And I have 4 nodes here and my k is also 3 here. So position from start I need to remove. In position from start means a number from start will be total node minus k. So here my total number of nodes minus n. Okay, so here my total node is 5 and 5 minus 2 3. So I need to remove 0 1 2 3. 0 based indexing 3. I need to go till 3th value and need that next pointer to move here. Okay, in this case also here my total node are 4. Okay, so that will work. So while my position, let's take a temporary variable as the head. While my position from start is greater than 0, I will move my temp pointer to next pointer and move this position. And at the last, what I will do is check if okay, if I need to remove that node, what I will do is move temps next pointer to temp dot next if temp dot next is not equal to null. Okay, so I think this will work. Okay, we have removed 5 here. So suppose we had total nodes 5 here and 5 minus 2 3. Okay, so here we have 3. Okay, so 3 is greater than 0. We'll move to this position. I think we need to go 1 point smaller. Okay, let's try submitting this. Okay, we have got a wrong answer. So here our slow pointer is at this position and fast pointer is also at this position. Fast pointer. Okay, so in this case my fast pointer is not null. Fast dot next is null, so number of node will be k is 1. Number of node will be 1. Okay, So position of from the start, position from start will be mm, 1 minus 1 is greater than 0. I think we should introduce a dummy node also. So let's do something like list node dummy is equals to uh, something like new list node. Let's see values in the description. Where is the value size? Node value -1. And dummy dot next as null. Sorry, as head. And temp we will take dummy. We will return dummy dot next. Let's see that failed case. Let's run. Let's submit. Okay, we have got a submission, so I think we should take a break now. We have solved two questions in a row, so yeah, I think this is a one pass solution. Let's see if someone has another one pass solution. Simple Java one pass. Okay, so I think this is the same solution. Okay, so I think our solution is pretty good. So we can move to next question. I think we should take a break now. This is a pretty good question. It was asked in many companies, I think so. Okay, let's see. Two numbers will be next question we'll be solving. Let's see my last submission. I think this year I have made a submission. No, last year I made a submission. Let's read out the problem. So the problem says a linked list of length n is given such that each node contains a additional random pointer which could point to any node in the list or null. So basically, this is our node. So this node has a value, and it will store two references. First reference to its next node, and second reference to a random node. Okay. So construct a deep copy of the list. The deep copy should consist of exactly n brand new nodes, where new nodes has its value set to the value of its corresponding original node. Both the next and random pointer of the new node should point to the new nodes in the copy list such that the pointer in the original list. Okay, so we just have to make a copy of this list, means a list which is exactly similar to exactly a copy of this list, but the all nodes will be new. We will not use existing node from that node, and all pointers should be pointing to the nodes with the values which they were pointing in the previous list. So that is a deep copy. Return the head of the copied list. Okay, the linked list represented in output input as of each node is representing a pair of where. Okay, random list, don't know what they are trying to say. An integer representing node dot value. Hmm. Okay, so I remember the approach to this question, which is inserting a new node against every node. So I will insert one node here, one node here, one node here, one node here, one node here. And we'll copy these pointers. Let's first just so basically current node is my head node. So what I will do is while my head pointer is not null, so I will store my head.next in this temporary pointer and will put a new node, create a this node new copy node, uh, new list node, which will have value exactly same as head dot value. And what I will do is I will move my times heads next pointer to this new node, and this new copy nodes next pointer to my temporary variable, and move my head pointer to next node. Okay, so what I have done is here is I have inserted a new node against each node. So for this example 7, I have inserted a node here with value 7, and I have moved this 7's next pointer. 7 is my head node, so its next pointer to this new node, and this new node's next pointer to my 13 node. So that is how I have inserted a new node against each node. So I can also confirm this thing. So let's not just list node temp is equals to head. Okay, so wherever we are using head, we will change it this temp, and wherever we are using this temp, we'll choose this temp 2. So we will assign new value. We will reassign temp to head, and while my temp is not null, temp dot value. Okay, and move my temp pointer to temp dot next pointer, and at the end I need to return some node. So let's just return a null for now. Mm, okay, so let's try to run this function. Okay, so we have got a error. So basically this is a node, not temp node. Next pointer of node with labels. Okay, so we don't care what we are getting output, but let's just focus on our printed value. So as we can see, we have printed one a node against each node. So against 11, against 10. So now we have new nodes. So basically, we will be now manipulating these values. Okay, so we have added a new node against each node. Okay, now we need to manipulate the what we can say is pointers, uh, random pointers. So let's figure out how we will move the random pointers. Instead of temp, we can just call it as current current to as temporary node. Okay. So here and here, assign to null. Okay. Now we move to here and here. Okay, it's pretty simple, I think. So now we will take two pointers. First one is to our old old list. So old list will be our at head position, and another pointer we will need our new list at our new list. So new list at will start from head or next position. Okay. So now we have two pointers. First is pointing to our old list head, and second is pointing toward our new list's head part. And at the end, okay, new list. Okay, current. Okay. Uh, do we? I am thinking that do we need to return the previous node into the same state? Mm, I think so. Let's for now let's start. So while my uh, old list doesn't become equal to null, I will move its pointer. So my old list's node will be one skipping then after that node. After one node of old list, I have a node of one new list. Then after that, I again have a old lists node. So my I need to move two pointers basically to move to next position. So old dot next. And similarly for new list. So currently I am at this position, so I need to manipulate random pointers. So new list dot what we are dot random pointer will point to old list dot if it's not null, if new list, if old list dot random pointer is not null, then in that case I will do this, otherwise it will remain random. So I will assign it as old list dot random dot next. Hmm, okay. We also need to detach our copy list from the original list. So let's see how we can do that in this same loop itself. So this is my old list, this is my new list. Okay, so I am taking this, considering this example. Okay, so my old list will go here. Okay. New list will go here. So after assigning the random pointers, suppose if I want to move my old pointer to means old lists, next pointer to new lists, next pointer, if my new list dot next pointer is not null, in that case I want to move my new lists next pointer to. So what I have done here is I have moved this pointer here, cutting this to this pointer here. This pointer here, and this pointer here. Okay. So my new list pointer will go to new list dot next. Okay, so what I am doing here is I am assigning random pointers here, and after that I am what I'm doing, I'm moving all lists next pointer to new lists next pointer. So new list next pointer will point next node of the old list. So I'm reassigning old list to its position, original position, and I will check that if my new lists next part, which is my old position, which is my old list, if it's not null, then I will access it next. That will be next part of my next list, and I'll move my list pointer to here. Similarly, my old list. I think this will work. Okay. Random pointer of node label 13 points to a node from the original list. Okay. I think I need to check this implementation against this. 7 is pointing towards 13. It's pointing towards 11. It's pointing towards 10. It's pointing towards 1. Okay, so random pointer of 7 is null. Random pointer of 13 is 7. Random pointer of 11 is 1, I think. Okay. And random pointer of 10 is at 11. Okay. And random pointer of 1 is at 7. Okay, so what I have done is I have inserted a node against each node, something like this, assigned to this to this to this, this to this, and this null to this. Okay. What's null? Okay. With values this. Now what I'm doing is I'm taking head as the old list and heads next as the new list. Okay, so at this point these values will be same, so we can confirm it just by printing the old list dot value if it equals to new list dot value, so we can confirm. So it's true, so we have values. Okay, and I'm then making this as new head, and at the end I'm returning this head. So now my old list, while my old list pointer is not null, what I will do is I will check my old list pointer. If it's not pointing to random pointer, I will pointing to null pointer, I will make it a random pointer. So in this initial case it's pointing to null. Now what I will do is I will move my old list next pointer to new list next pointer. Okay, I have moved. Now if I will check if my next pointer of the new list is not null, so it's not null. Okay, if it's not null, then what I will do is I will move new list's next pointer, assign it to next pointers next. So okay, I am doing this. Now my new list will become new list dot next, which is this, and my old list will become old list dot next, this pointer. Okay, now again I will check my old list is not null. I will move my old list random value to check if it's not equal to null. No, it's not equal to null. Okay, in this way I'm disrupting my. Okay, I think I should first just assign random pointers. Okay, so I have assigned random pointers. This was insertion. This was assign random pointers. So I have assigned random pointers. Now I need to separate my new list. So what I will do is I will initialize list node new head. Mm, new head as head dot next. While my new head dot next is not equals to null, what I will do is, so let's reassign this pointer, reuse this pointer. I'm reusing this pointer. So while my new list dot next is not equal to null, what I will do is I will move my new list next to new list dot next dot next. Okay, In that way, this will give my new list to me. In this case, I will break my loop because I don't have a next node to the new list node. Okay, so I need to return the original list as it is. So my old list pointer is this. So what I will do here is node next old node. Next old node will be new list or next. Okay. I will modify this node and make my old list dot next as next old node. Okay. I have made it to next old node and move my. Okay, I moved this pointer to next node. And at the end, I will move my old list dot next. While my old list next is not equal to null. New list dot next is not equal to null. Suppose I have this example. Old list is at head, new list at this position. What I will do is switch to this pointer. I will. This is my next old node. My new list move to this pointer. My old pointer to this pointer. I think this will work. This is my new list. This is my old list. I will check if my new list dot next is not null. It's not null. My next node will be new list dot next. Okay, this now I have a pointer old node here. Old next. What I will do is old's next to new list dot next not next. Okay, move here. Move new list to new list dot next. Okay, new list is this pointer now. Mm, and old list dot next will be this. Next will be this pointer. I need to move old it not next. Old list to old list next old node. Mm, okay, so I think it's now working. Let's try submitting this. D attach detach list. So basically it is failing when our head is null. So if head equals to null, then we can return head. Okay. Okay. So I think this was the approach. Let's see at previous submissions. So in the previous submission, I have used a map. Okay, using map to put the values. Mm, I think this approach we have used now is the most optimized approach. Okay. Okay, so I think this will be the last question we will be solving. Add two numbers. So you are given two non-empty linked lists representing two non-negative integers. The digits are stored in reverse order, and each of their nodes contain a single digit. Add the two numbers and return the sum. So basically, we have a number stored in reverse order. So this is 343. Sorry, 342. First number is 342. 342. We need to add in it 465. 465. So answer will be 10 7 8 8 0 7, I guess. Okay, so 807. So basically this is ones part, this is tens part of the digit. So we need to return a list node 807. So okay, so I think the list can contain different number of nodes. Means this can represent a 4-digit number, this list can represent a 3-digit number, and we are starting from ones position. And we need to add the list. So 4 3 2 1 3 2 1. Okay. So I think this is not that tough. We can do it in one pass only. So suppose we have a list representing number 1000. So the list will be something like 0 0 0 and 1. Okay. So and in this number we need to add suppose we need to add 99. So that 99, let's say 89. So 89 will be represented by 8. 89 will be represented by 9 and 8 in reverse order. So basically this is representing 1000, and this is representing 89. So our output should be 1089. Okay. So what we need to do in addition is we need to add ones position 0 with 9. Okay. So let's say this one 1001. So we can also explain the carry part. So in mm, okay, in addition what we will do is we will add the numbers at the ones position. So their sum is 10. So we have got a 0. Okay. We have got a 0, and we have a carry of 1. So we have a 1 carry here. We will add 0, 8 plus 0, which is 8, and we'll add carry, which is uh, which makes our total sum to 9. Okay. Then we move to next part. So here our next pointer will become null, and we can just move to rest of the part as our carry is 1. So this will be output. So it is pretty simple. So we have L1 and L2. Okay, so while L1 is not equal to null and L2 is not equal to null, let's define our list node. Hmm, answer as the uh, let's define it as a dummy node, new list node. So let's define it as something like we can have values. So our values can be node dot value can be 0 to, so we let's define with -1. So this is our answer node, and let's take a temporary iterator to this answer node, and at the end we will be returning answer dot next. Okay. So our current value at position, this is L1 dot value 1 is, and value 2 will be L2 dot value. Okay. We also need to define a carry. So initially our carry will be 0. So and after that our digit will be val1 plus val2 plus carry divided by 10. Okay, divided by 10. And for example we have 16, so 16 divided by 10 will have 6 and 1 as the carry. Okay, so our carry will be this is our digit for which we need to create a and our carry will be I think divided by 10. So suppose we have 16 and 16 divided by 10 is 1. We have 9, 9 divided by, okay, so we have a carry like this. And we can put our answer dot next node as new list node which will have a value of the digit. So yeah, and we can move our answer to, sorry, iterator. We are using iterator, so we can move our iterator to iterator dot next position. And similarly our l1 to l1 dot next position, and l2 to l2 dot next position. Okay, so suppose if our digit was like something, suppose if our l1 becomes null, so we need to iterate rest of the l2. If our l2 becomes null, then we need to iterate rest of the l1. So do can we handle it in the same loop? Okay. Let's say I handle in the same loop. So if my l1 becomes equals to null, then in that case what I will do is I will give 0. Otherwise I will store this value. And similarly for l2, if my l2 becomes null, in that case I will use as value as 0, and otherwise I will use its value. And in the case if my l1 is not equal to null, I will move it to the next part. If my l2 is not equal to null, then I will move it to the next part. If my both becomes null, then I have iterated the full list. So I think this will work. Okay, one possibility can also happen, like if I have two lists. Suppose first list L1 is 5 and list 2 is also 5. So my L1 pointer is here and L2 pointer is here. So in that case, my carry will remain as 1. So if my carry is not equal to 0, in that case also I need to iterator dot next new list node I need to add. Okay, so I think we have covered all the cases. Let's run this. Okay, we are getting an error. We have left some explanation. Okay, so what we are getting, we have a list node. Okay, we are getting correct output. Let's try submitting it. Okay, we have found a submission. That's great. So we simply have manipulated basic addition which we were taught in school into the list nodes, into the node part. Okay, so can we solve one more question? No, we cannot. We have only 6% battery remaining. Find the duplicate number. So we have given a list. We need to find a duplicate number. So wait, it's a array. Given an array of integer containing n plus m integers. So I think this was supposed to be a linked list question, but it's a array question, and we need to find a duplicate in it. There is one repeated number. Return this repeated number. You must solve problem without modifying the array nums and using only constant extra space. Okay. Given an array nums containing n plus 1 integers, where each integer is in range. Okay, okay, understood. So basically, in our array, our integers are in range 1 to n. So where suppose our array has size 5. So our integers are in range 1 to 5. I think that's what question is saying. Nums containing n plus 1 integers, where each integer is in range and one integer is repeating. Okay, and we need to find the repeated element, and we need to solve it in constant extra space. Okay, so our array size is 5, 3 to 5, n plus 1, containing n plus 1 integer. Okay, so we have n plus 1 integer. So if our array size is 5, so that means n plus 1 is 5. So in that case, n will become equal to 4. So our numbers in this array can be in between 1 and 4. Okay, our number can be in between 1 and 4, and we need to find a duplicate number. So we can use a slow and fast pointer approach here, because our numbers which are present in the array are within the indexes ranges. So this suppose I am at 0th index currently. So I need to move at 1th index. I have moved at this index 1. Okay. Now I need to move at index 3. Okay. Now I need to move at index 2. Okay. Now I need to move at index uh, 4, 0, 1, 2, 3, 4. Okay, now I need to move at index 2. Now I need to move index 4. So basically we have a cycle. So we need to detect a cycle, and for cycle detection in linked list, we can use a slow and fast pointer approach. And the head of the basically cycle will be our answer. So we will solve this question in the next stream. This question and these three questions. So that is it for today, guys. Thank you, guys. And stream.